Hello, I'm Zach, and in this lab we will be configuring IP SLA. Briefly, before we start, I would like to talk about what IP SLA is. IP SLA is a Cisco proprietary technology that is essentially a testing mechanism that is used to validate service uptime. Now we know SLA stands for Service Level Agreement, which is a contract between a customer and a service provider for a minimum level of performance. So IP SLA is an active mechanism that generates and monitors traffic continuously in a network. And with that information, you are able to make decisions, for example, where to route traffic. Here I have an extract from a Cisco white paper where Cisco clearly defines what IP SLA is. Now there are numerous operations that you may perform in IP SLA. One of them is CCNP echo, which measures the response time between a Cisco device and any IP device. So essentially it's the time between the ICMP echo request and the ICMP echo reply. Another example is UDP jitter, which measures real-time traffic. Okay, so real-time traffic apps. For example, you have VoIP, which is voice over IP. Another example is real-time conferencing. Some of these operations do require a responder, which is configured on the target router, and the responder allows you to increase the accuracy of the measurements. One-way delay measurements only have 2 timestamps on the target router. It is recommended though to sync the NTP, the network time protocol, between the source and target routers to get the most accurate results and measurements. Now, before I start the lab, this is the topology that we will be working with, where you have one customer edge router, which in real life could be a hospital or a university or any enterprise, that is connected over 2 separate links to 2 different ISPs, with the link towards ISP1 being the primary link and the link towards ISP2 being the secondary or backup link, were the primary link to fail. Okay, the first thing we'll do in this lab is to ensure that all of the interfaces have been pre-configured correctly so that it matches the topology. That looks correct. That looks fine. Finally, if I check the second ISP router, excellent. So now that we know that all of the interfaces have been pre-configured correctly, what we need to do is create 2 static routes. As we know here, the customer edge, which could be a university, a hospital, or any other enterprise customer, has 2 WAN links or 2 links towards 2 separate internet service providers. The link towards ISP1 will be our main link where all of our traffic will go, and in case that was to fail, we'll be using this G01 link towards ISP2. So if we create a static route for our main link first, so any traffic generated will be forwarded to ISP1. If we do the same thing now for ISP2, but with a twist. Were I to enter this command now, what would happen would be that the traffic sourced from here would be load balanced across both of these links. But that's not what we want. What we want is for the traffic to primarily go through here, and in case it failed over, to come here. So I would have to assign this route, this static route, with an administrative distance greater than the standard administrative distance of static routes, which is 1. So if I give it any number above 1, this will make it a floating static route. So that means essentially it's in the background waiting to take over in case this static route were to fail. We can see now, if we were to shut down the interface headed towards ISP1, interface G00, the actual routing table would change. Before I do that, if I just show you the routing table, as we can see, the only static route in the routing table is pointing towards ISP1, and it has an AD, or administrative distance, of 1. If we shut that interface down now, it should fail over to ISP2, so the routing table should be updated. If we check that now, there we go. Now the floating static route has been installed into the routing table. It has a higher AD, and it is now heading or pointing towards ISP2. So the traffic is now going towards ISP2 because this interface here that's pointing towards ISP1 is being shut. Okay, so there is some limitation to this because let's say, for instance, both of the links local to CE were working, but the actual routers, ISP1 for example, let's just say that it was unavailable or it was not working correctly, the IP route would not be able to tell. It would still be up, it would still route the traffic towards ISP1. That's why using IP SLA and object tracking together is the best way to ensure failover in case there are changes to the source and the target routers. So if I set up my IP SLA operation here, I will be using the operation TCP connect to ensure that there's TCP connection between the two routers. It measures, TCP connect actually measures the response time for TCP connect between a Cisco device and any IP device. Ideally, you'd like to have a responder on the other side, which increases the accuracy and the accuracy of the measurements. So if I start this process here, and I'm targeting the ISP1 router, it says here to use ports greater than 1023. So any ports that is 1023 or less are known as the well-known ports, the common ports. So you have to use one that is sort of custom. So I'll go for the 1234, easy to remember. And the control is essentially when you have an IP SLA responder on the other side, or your target router in this scenario, which is ISP1, you would like to actually enable the control protocol. But if you just have a end host, for example, then it's better to disable, or you're supposed to disable the control protocol. But in this case, our target is another Cisco device that is going to enable responder in a minute. So we can enable that, that's fine. And here we have some factors that we can play around with depending on what we want, including frequency, threshold, and timeout. So if I just start with threshold at first, and I make it, I believe it's in milliseconds, yeah, 1000 milliseconds. And I also change the timeout to, let's say, 200. So this is the maximum time that the message can take to come, or the response time before failing. So as long as it's less than 200, that's fine. Or let's say 2000 milliseconds. As long as it's less than 2000 milliseconds, then it should be fine. Finally, if I make the frequency every 2 seconds, so every 2 seconds we'll be generating IP SLA to the other side Okay, so you can play around with that, but I've kept it fairly simple there. So now, if we actually start the IP SLA operation with this command here, IP SLA schedule, for the entry number 1, we can start immediately, and we can also determine how long that this operation will last. In my case, I'll make it forever. Okay, so as far as this router is concerned now, the source router, we're ready to go. So if I also do some configuration here on the target router. So if we enable the general IP SLA responder on the target router ISP1, and then also enable ISP IP SLA responder specifically about the operation that we initiated on the source router. If you remember correctly, we used port 1234, which is outside the well-known range ports. So now we should be getting traffic. If I check the IP SLA responder, there you go. So we've already had messages or probes from the customer edge router, as you can see from the IP address. If I go back to the customer router, I can check the statistics. If I go to the customer edge router, that was a mistake on my part. There you go. So we've had a lot of successes so far. We've had it in way less than the timeout that we set. So it's very quick. So everything looks good on this side. We are generating exactly what we want to generate. However, we have an issue. We need to associate the IP SLA with the route, the IP route that we put in earlier. So if I show you that now, if you remember earlier, we put in these routes, these two static routes, one pointing towards ISP1, the other pointing towards ISP2. We must remove the original IP route and re-enter it, but this time associating it with the IP SLA via object tracking. Let me show you what I mean here. So at first I will remove the original static route. If I re-enter it this time, but with a tracking object. Apologies, I experienced some technical difficulties with Cisco Modeling Labs. However, now we are ready to resume. So if I just verify that the original configuration I put in earlier is still available on the router. Let's check the static routes first. There we have it. We have our secondary static route with a high AD leading towards ISP2, and we have our primary IP route heading towards ISP1. So all traffic generated prefers this route first, and it also has a tracking object associated with it. If I do the same thing just to make sure that the IP SLA operation is also configured on the router, customer edge router, there we have it. Okay, so the next step we need to take now is to actually create the tracked object. Okay, so object tracking, quite simply put, it acts as a glue in this scenario. It is the thing that sticks together and brings together the IP SLA and the static route. Okay, so if I do that now, I associate it, and we are looking for reachability. This is what we are looking for, okay, between the two routers, CE and ISP1. Okay, so now with object tracking and IP SLA, if the interface on this router here, the internet service provider, our main internet service provider, goes down, or the router is no longer available, or quite simply put, if reachability is no longer possible when IP SLA generates the probes to ISP1, if it does not achieve reachability, then what would happen is failover towards the second WAN link to ISP2. Okay, so object tracking helps us achieve that. Prior to object tracking, earlier in the lab, we only were using static routes, okay? And with static routes, it only considers the local interface on the router. Were ISP1 to fail or be unavailable, IP static routing would not be able to failover at that point. So object tracking allows us to make sure that this link is always up and working by sending probes using the TCP connect operation. So if I just shut the interface down on this side now, this is the interface that leads to customer edge. What should happen is object tracking should recognize this. It should go down to the track status down, and failover should happen to ISP2. So now the customer edge can access the internet via ISP2. So if I shut it down, go back to the main router. Okay, we can check the actual routing table now before that happens. As you can see, currently we have this route, this static route that sends all traffic generated here towards ISP1, as you can see, and it has an AD of 1, which is the standard or default for static routes. Now though, we have a syslog message with a severity level 6, which is informational, that is informing us of the change of track status from up to down. So our routing table should be updated now, okay, with a new static route installed into the table heading towards ISP2, which was previously our floating static route. So if I show you here, they should now install this floating static route into the routing table because reachability is no longer possible towards ISP1. We must now use ISP2. If I just verify that by checking the routing table again, there we have it. Now to access the internet, we will be using ISP2 from the customer edge's point of view with a higher AD of 2. So any traffic generated now will be heading towards ISP2. So this is the benefit of using object tracking. Okay, it helps us to ensure that if connectivity or something changes, that we have a response prepared. I hope you have learned something from this lab configuring IP SLA. Do stay tuned in for more.